Hey there, I'm Callan Bentley, and the point of this video is to take you on a brief stratigraphic tour through the different formations that make up the rock units here at Glacier National Park. So we're going to start at the bottom, and then we're going to work our way up through the stratigraphic sequence so we get a better understanding of how the rock formed that was carved into these magnificent shapes like you see here behind me. Alright, so let's begin. The lowest of the stratigraphic layers within Glacier National Park is the one we want to start with, because that's the oldest one. And that's what you see here in this road cut behind me. I'm here at Upper St. Mary Lake, at one of the first rock outcrops that you see as you drive going to the Sun Road, going from east to west. And what you see is some dipping white layers, and these are of a rock type called dolostone. This is the Altyn Formation, and it is only present here on the east side of the park. If you go to the west side of the park, there's another formation at that same level, the Pritchard Formation. I'm not going to focus on that at all, but this is a carbonate unit. Limestone and dolostone, mainly dolostone here, and in places it's got some stromatolites, in other places it's got a significant sandy component, and here there's actually a fair amount of quartz sand in it as well. We would probably guess, based on the thickness of the layers, which are relatively substantial, and the fact that it's carbonate dominated, that it wasn't too close to any significant source of siliciclastic input. So no major landmass nearby that would be weathering and eroding and generating sand and mud. Instead, basically what we have here are ions linking up in the seawater and crystallizing out to make this carbonate sediment. So this is different from limestones that are made out of biological material that are found at later times in Earth history. This is an inorganic precipitate, and it's called the Altyn Formation. In places, the Altyn Formation has a fair amount of sand in it, so these gray colored grains that you see here in these lines, those are sandy inclusions within the overall dolostone. Sometimes they show cross-bedding, like you can see here, and sometimes they can actually be pretty substantial. So here's an example of that. Here's a boulder where it's mainly dolostone, but then there's a really thick sand layer. And in fact, some of these sand grains are so big they're not even sand grains. These are essentially pebbles. So periodically there were high energy events that brought in sand, yet strangely did not bring in much in the way of mud. So the Altyn Formation has both carbonate and a fair amount of quartz sand in it. The next formation up in the stratigraphic sequence is the green rock you see here behind me. This is the Appekunny Formation. The Appekunny Formation is very thick. It's much thicker than the Altyn Formation, something like 2,700 feet thick. And it's mainly green argillite. So deposits of mud in the Belt Sea, but the mud that was deposited here was deposited in an anoxic environment, so there was no oxidation of any iron that was present, even though these green rocks contain exactly the same amount of iron as you'll find in the red argillite of the next formation up, the Grinnell Formation. Both about 3% of the rock's volume is iron. But here it was deposited under low oxygen conditions, and when the belt strata were buried in the earth, they underwent a very low-grade form of metamorphism. This was not like mountain building metamorphism that makes mica grow or garnets or anything like that. The primary sedimentary features, like the bedding that you can see here running along at a gentle angle behind me, that's all basically not been destroyed. So this was very low levels of metamorphism, burial metamorphism, but it was sufficient to grow this green mineral, chlorite. So the green color you see here comes from the mineral chlorite. That's actually a secondary mineral. These would not have been green when you, if you were able to go back in time and see them at the moment of deposition. But let's take a look at some of the detailed primary sedimentary structures we find in this unit. The first thing that you'll notice when you look in detail at the Appekunny Formation is that it's fine-grained and it's finely layered. So within the outcrop behind me, you can see there's some little fracture surface lines that you can see right here. Ignore those for a second and focus in here at these sort of almost layers of paint thin, less than a millimeter thin layers of sediment. So in order to get layers of sediment that are that thin and made of such super fine-grained material, you need a couple of things to be true. One is you need a source of that mud, all right? So that mud has to come from somewhere. And it's basically coming from the weathering and erosion of some land somewhere, okay? So this implies a source of siliciclastic material coming into the Belt Sea that is subsequent to the carbonate-dominated deposition that we see lower down in the Altyn Formation. But it's not like there's full-on raging mountain building going on nearby, because these are very, very, very small particles. And the fact that they're deposited in such thin layers indicates very calm deposition. So this was probably deep water below wave base. When you get up higher in the Appekunny, you get some indications of shallow water conditions. But at this point in the Appekunny, it's basically deep water, very calm water, but there is a little bit of material coming in from some landmass somewhere nearby. So here are some of those extremely thin layers, all right? Very, very small, indicating very, very calm water at the time of deposition. Otherwise, the tiny little flakes would never have settled out. In addition, if the water was very energetic at all, we'd expect to see erosional structures that cut into these delicate little laminations. Another thing you can see here is that there are a few spots where we've got stringers of quartz sand that run through the rock. So there is a little bit of quartzite within the Appekunny Formation, like right here. All right, this is an example of some of the primary sedimentary structures you see up near the top of the Appekunny Formation. This is looking down at the bedding plane. These are mud cracks or desiccation cracks. So obviously it would have had to have gotten shallow in order for the mud to be exposed to the air and dry out. From the side, those mud cracks look like this, these little V-shaped notches into some of those argillite layers. Also, here's some nice cross bedding, indicating higher energy conditions. The next layer up in the stratigraphic sequence is the Grinnell Formation. It's a very distinctive layer, blood red, well, maybe more of a maroon, but it's also got a significant percentage of sand in it, so there's white quartzite layers throughout. It's got a wealth of primary sedimentary structures that indicate it was deposited close to shore in shallow water conditions. So we got things like mud cracks, mud chip rip-up class, cross bedding. These are all basically shallow water indicators, high energy indicators. The sand itself also indicates high energy because that's a bigger particle size than the fine grains of the mud. So here's a fairly typical look at a cross-sectional view through the Grinnell Formation. We've got some nice cross beds here at the bottom. We've got a muddier layer, but it's mainly made of mud chip rip-up clasts. These mud chip rip-up clasts are really prominent here with nice angular shapes. Here's an example of one of the bedding planes of the Grinnell Formation, and you can see that it's got really well-developed mud cracks all over its surface. These are desiccation features that happened when the mud, which was deposited in water, found itself then exposed to the air and drying out. And as a result, it shrank a bit as it lost volume due to evaporation. As it shrank, it broke. The individual polygons of mud pulled away from one another. So you can see some of these polygons here, sort of defined by the mud cracks on either side. Here's a polygon with mud crack, mud crack, mud crack, defining its edges. So in this case, they pulled apart from one another. They opened up these little V-shaped gaps that went downward into the body of mud. And then in this case, mud was deposited filling in the gaps. Other times we see sand filling in the gaps between the polygons of mud. Here's an example of some of the desiccation cracks, the mud cracks, where the gaps between the mud polygons have been filled in by sand deposits instead. So we're actually looking at the bottom here of a quartzite layer filling in the gaps between a previously deposited mud layer. Well, this outcrop here showcases one of my favorite primary sedimentary structures within the Grinnell Formation. And if you look over here, we've got a layer of quartzite, which is bright white. And of course, there's also some red argillite. But then within the white quartzite, we've got these round balls of red. So these are mud chip rip-up clasts, kind of like these ones over here that have more angular shapes. But these round ones apparently have been tumbled quite a distance. In places, the Grinnell Formation shows a well-developed tectonic cleavage. That's true for this outcrop here behind me. You can see sedimentary layers dipping, defined by the difference in grain size, the sand versus the mud. But then you can see a steeper fabric element dipping through the rock as well, and that is the tectonic cleavage. It makes the steeper slope here that makes this outcrop kind of weather in steeper and more gently sloped arrangements. So that's a tectonic cleavage, and that was developed in these rocks at the same time as transport along the Lewis thrust, folding. It's basically a symptom, a deformational symptom of the severe orogeny. The Empire Formation is a transitional formation between the Grinnell Formation and the next formation higher in the sequence. And that's what you see here behind me. This is the Helena Formation. It's a carbonate-dominated unit, mainly limestone, some dolostone too. It has a sort of dark blue-gray kind of color when it's fresh, when the rock is freshly exposed. But then over time it weathers and it develops this very attractive sort of buff-colored or honey-colored weathering rind on the outer surface. So this is a return to more offshore conditions, not a huge amount of siliciclastic input in the Helena Formation. Occasionally you'll find some sand in it. But the Helena Formation is neat because it's nice and thick, 2,700 feet thick. And it's chock full of really interesting primary sedimentary structures. These include ooids, which are little carbonate grains that form inorganically due to precipitation from supersaturated seawater. And then we've also got stromatolites. We'll take a look at those here in a moment. And an interesting structure called molar tooth structure, which we're not really sure quite how it forms. There's really no analog for it in the modern world, so it's a little bit enigmatic. But it's also an interesting texture you often find in the Helena Formation. These are some of the justifiably famous stromatolites that you find within the Helena Formation. It's really cool to be able to get this view back in time to these primordial organisms that were the main form of life on the planet Earth for a long time. Microbes, but microbes that had discovered photosynthesis and were capable of suturing carbon dioxide molecules from the air to water molecules from their surroundings and making sugars that they were able to then break and release the energy from and use that energy to grow and to reproduce and all that kind of good stuff that life likes to do. Within the Helena Formation, there are these certain horizons that are really rich in fossil microbial mats, stromatolites. And you can see some on the wall here behind me. The dome-like shapes that you see are laminations that are not folded. This isn't some sort of tectonic folding or anything like that. It's instead the actual shape of these things at the time that they originally formed on the seafloor. So they domed upward towards the sunlight. They were photosynthetic slime, cyanobacteria. And this is actually their shape as they grew on the seafloor. They basically tell of a time when the planet Earth was a slime world, when there were no animals, no plants, no eukaryotic organisms even, but these prokaryotic microbes had figured out photosynthesis, and living in the shallow water where the sunlight was able to penetrate to the bottom, they were able to grow and make these sorts of structures. Well, I'm just downhill of the West Side Tunnel on the Going to the Sun Road, and both downhill and uphill of me there are plenty of outcrops of Helena Formation limestone. But right here behind me you see something that looks quite different. It's dark colored and kind of speckled. If you look closely you'll see that the speckles have sort of a 50-50 proportion of light and dark. The dark stuff is a mineral called pyroxene, and the light stuff is a mineral called feldspar. Together these make up an igneous rock that's called diorite. If you look closely here, you can see the sort of salt and pepper arrangement of the minerals here in the diorite. So we've got about equal proportions of light and dark minerals. They are visible to the naked eye, and that implies that they cooled slowly underground over a long period of time. In many places within the sill, you can see some alteration that's produced a green color. That's a metamorphic mineral called epidote that occurs when we have pyroxene and plagioclase feldspar interacting under metamorphic conditions with water. And so it's a distinctive colored mineral that we often find in this rock. And this is an intermediate composition rock that formed from intermediate composition magma that was maybe about 60% silica, but was reasonably enhanced with iron and magnesium. And that was intruded into the pre-existing sedimentary layers of Glacier National Park, particularly the Helena Formation, around 750 million years ago. In other words, it's Neoproterozoic in age. It makes a prominent sill that can be seen as a dark stripe running through high peaks throughout the park. The rock layers of the Helena Formation immediately above and below both got cooked by the intrusion of the magma. So the magma had lots of heat in it, and it altered those rocks. So they were contact metamorphosed, and that mainly shows up as sort of a bleaching. So while most of the story of Glacier National Park is the story of sedimentary deposition, followed by tectonic activity, followed by glaciation, this is the exception to the rule. This is an igneous intrusion that occurred between the deposition of the sediment and the severe orogeny. All right, here I am. I'm on the uphill side of the tunnel on the east side of the park, just below Logan Pass. And you can see behind me a contact between two very different colored and textured rock units. The upper one is the Helena Formation, but it's been contact metamorphosed. So it's bleached to a whiter look than it usually has. Remember that the Helena Formation typically has sort of a bluish gray coloration, and then it weathers to a tan or honey kind of color. Down below, though, we see what cooked it, what was the source of the contact metamorphism. And this dark colored rock that you see right here is the sill. All right, so that is a batch of magma that intruded between the pre-existing sedimentary layers of the Helena Formation sometime around 750 million years ago, prying them apart and then slowly cooling and congealing and solidifying to become this solid igneous rock called diorite. So I'm just a little bit below the hairpin turn that they call the loop over on the west side. And behind me you can see an outcrop of siltite and argillite. There's a little bit of quartzite in here too, so if you look down here you can see there's some nice sandy layers. So this is the next layer up in the sequence. It's also present up by Logan Pass. This is called the Snowslip Formation. And the Snowslip Formation is sort of a grab bag of different lithologies, mainly argillite and fine-grained sediment, some quartzite in there as well, but also some carbonate. And there are even some stromatolites within it. So it's kind of a mix of many of the different features that we've seen in earlier, older formations. Here's kind of a cool contact where you can see that older muddy layers were eroded into and hence truncated by a high energy event. That high energy event also brought in sand, so you can see there's some nice sand grains here making a little layer of quartzite, and it also ripped up chunks of the mud so that we've got these mud chip rip-up clasts as well. So as we go along this layer, we can see that this must have been a time of relatively high energy in what was otherwise a pretty calm environment. So here we can see some really thin laminations, and then disrupting these laminations, little mud cracks like right here and right up here. Those mud cracks are an indication that this was exposed to the air for some period of time. And so one pretty solid interpretation for the Snowslip Formation is a series of tidal flat deposits. Here's a pretty cool primary sedimentary structure. This is a train of ripples with internal cross-bedding that you can see here preserved in this layer. This probably represents a time of the tide coming in or the tide going out, and that extra energy to the current ended up building up ripples. This particular train of ripples prograded from the right side of the screen toward the left, so they were moving in this direction, and each little layer that you see here represents a deposit on the downstream side of the migrating ripple. So within the Snowslip Formation, you know, because it was sort of siliciclastically dominated, there were times when water level was higher and stromatolites were able to start forming. But all that mud basically overwhelms the stromatolites, and they don't tend to really thrive in an environment where there's lots of mud. You can get other primary sedimentary structures called microbially induced sedimentary structures and siliciclastic rocks. But anyhow, behind me is an example of some of the stromatolites, which are unusually colorful within the Snowslip Formation. Some stromatolites that got established, grew into nice little domes, but then basically were smothered by mud. Well, there are also surficial deposits in the area of Glacier National Park, and I like to organize these surficial deposits into one of three categories. The first category is what you see here on the hill behind me. This is an extremely poorly sorted sedimentary deposit, and you can see great big pieces mixed in with really tiny little pieces. The lithologies are quite mixed up, so you've got lots of different rock types here. And yeah, there's a lot of really fine things in here as well. Notice also the clast shapes. They are often faceted, like this boulder that you see over here behind me. That means that they've been basically ground down, not pulverized, but ground down against the landscape and been transported along by glaciers. All right, so this is an example of glacial till here behind me. And it's distinct from the other two surficial sedimentary deposits, which are colluvium and alluvium.